the observation we can make here is that this language is really the intersection of two simpler languages. And so if, in general, we are trying to build a machine that recognizes a set that happens to be the intersection of two languages, then we could think about how solving the problem of building machines that recognize each of the simpler sets can get us closer to a solution that we want. And when we think about the roles that we had for each of the states in the machine that we just built, in each one of these roles, our states had to record information about both pieces of the pattern we cared about. We had to think both about parity and our progress towards the substring. So Q0 told us where we were about our substring as well as where we were about the parity. And in a sense, what we're doing here is running basically two DFAs in parallel. So what we would like to think about is having a single DFA that under the hood is acting like running M1 and M2 at the same time. Now, our DFAs don't really work like that. Right now, in our DFAs, we have a model of just like a single state that we're in. And as we process symbols from the outside, we're making choices about how to change our state of the machine based on that stimulus. So we're going to need to encode all the relevant information about M1 and M2 in each state of the machine M that we're building. For this running in parallel, if our states are going to have to encode everything there is to know about the state we are in M1 and everything there is to know about the state we are in M2, how many states will we need for M? And we seem to be drifting towards C. And in this case, C indeed is the right answer. I know, people are like, whoa, what's going on there? If we want to keep track of what's happening in M1 at the same time as keeping track of what's happening in M2, then enumerating all the possibilities of having one of the states in M1 it being something that we remember, and one of the states in M2 being something that we remember, we have to think about like all of the ordered pairs where the first component is coming from M1 and the second component is coming from M2. We need to think about all of the pairs of states that we could, the two machines could respectively be in. And so the construction that we're doing here is the Cartesian product construction. So, whoa, that was exciting. We're going to build M to have as its set of states Q1 Cartesian product with Q2. And the size of the Cartesian product is the product of the sizes of the two sets that we're keeping track of. And our alphabet is the same as before. We're going to think of what the transition function is going to look like. So that we'll define in a minute. What's the start state of this machine? Now, we're in this part of the room. Yeah, go for it, Maria. It's exactly that, the ordered pair of Q1 and Q2. So if we gave ourselves M1 and M2 as the DFAs that recognize those two parts of our pattern, they recognize the sets that we're intersecting together to get the set we care about, then the ordered pair that records, hey, I'm at the start state of the first machine at the same time as being at the start state of the second machine, is the start state of this composite machine. Okay? Yeah, go for it. Is there a reason why order matters? Great point. Yes and no. So we have to pick an order. It doesn't really matter which one we pick, but we've got to stick with it. Because if we have any repetition in the labels of the states, we need to know which of the machines the state that we're looking at comes from. So we can't do unordered sets, but we could have done like M2 cross M1. We could have done Q2 cross Q1 or Q1 cross Q2. That doesn't matter. Yeah, good point. Thank you. All right. What about the set of accept states? Let's talk about that. And I think we're in this part of the room now. Yeah, go for it. Cool. F1, take its Cartesian product with F2. And the reason for that is we want our new machine to accept a string if the computation of the new machine lands in a state that represents both of the machines M1 and M2 being happy. Okay? So that means that the first component of the state needs to come from the set of accept states of M1, and the second component of the state needs to come from the set of accept states of M2. Okay? So then we should write down what the transition function looks like. So the transition function, whoa, don't do that. Do you know why it went to a triangle, by the way? What was PowerPoint trying to help me with? It's capitalizing. So triangle is capital delta. So that was the auto-capitalization of PowerPoint in Greek. All right. So delta is accepting an ordered pair. And here we're going to get a profusion of parentheses, because delta is a function that we apply. So we've got this outer set of parentheses for saying we've got function application. And the input to the transition function is an ordered pair, which is some state and some symbol from our alphabet. Okay, so we're going to define this where A is an element of the alphabet, sigma. And the first component of this ordered pair that we feed into delta is supposed to be a state of our machine. Now, in our machine M that we're building, states are ordered pairs. So that first component is R1, comma R2. Okay? So here R1 is an element of Q1, and R2 is an element of Q2. Now we get to define this transition function. Once we've spelled out all the symbols, bless you, how do we define the output of the transition function, so the next state in this composite machine, if we were in R1, comma R2, so M1's in R1, M2 is in R2, and we read the input symbol A. So states in M are elements of Q1 cross Q2. What do elements of Q1 cross Q2 look like? Ordered pairs. So we've got to specify the ordered pair that we go to, where the first component is going to come from Q1 and the second component is going to come from Q2. How do we know which state in Q1 we land in? This machine is supposed to simulate M1 and simulate M2. Yeah, go for it. Awesome. So this component is telling us about what M1 does. And so we want to record here the state that M1 would go to if it was in R1 and read A. Okay. So if we're in M1 and we read A, what M1 does is apply the transition function delta 1 to the state R1 reading A. Okay. And similarly, M2 is going to apply its transition function delta 2 to the state R2 reading the very same symbol. Okay, so that's what we mean when we say running in parallel. Oh, great question. So you're saying, what if the pattern that M1 is detecting is saying, I want strings whose length is even, and what if the pattern that M2 is detecting is I want strings whose length is a multiple of 4? Then the intersection of those two is going to be the language recognized by M2, right? Because if I've got length 4, I'm already even. And so maybe I don't even need to do this big Cartesian product thing. I don't need as many states as the number of states in M1 times the number of states in M2. I could do just as well with taking the number of the states in M2 and be done with it. And you're right that for specific examples, this construction will be like a big hammer to solve a small problem. What this gives for us is a general approach to solving complex DFA design problems if we can't think of a nice shortcut of describing their language more simply that will let us attack it directly. Now, there will often be optimizations that we could do after we do the general construction to make our automaton smaller. But what this means is that no matter what our language is, if we can express it as the intersection of two sets, then we have an incremental approach to coming up with a DFA for recognizing that language.